call what we said was that if H a Hermitian matrix, so A Hermitian matrix, we saw if A has distinct, so all distinct eigenvalues. Then it's better than just diagonalizable. Right? I mean, this statement is true even without the Hermitian part. Right? If you leave Hermitian off, any matrix with all distinct eigenvalues is diagonalizable. Right? But we have something better. If it's Hermitian and it has all distinct eigenvalues, then in fact it's unitarily diagonalizable. Right? That there's a unitary matrix. There's a unitary matrix, and remember what unitary meant, right? It's basically the analog of orthonormal, right? But with complex matrices. So it's unitarily diagonalizable. Okay, so there'd be a unitary matrix so that U inverse AU is a diagonal matrix. Okay, and we said that in fact there's something better, and that better thing is called the spectral theorem. Spectral theorem. So it has this cool name, the spectral theorem. It doesn't have to do with ghosts. It has to do with the word spectrum. Spectrum is the term used to describe the collection of eigenvalues. Okay, so you say the spectrum of A, that just means all eigenvalues of A. So spectrum. There's this thing called the spectral theorem that says, in fact, that every Hermitian matrix is unitarily diagonalizable. Unitarily diagonalizable. Okay, so you don't have to have distinct eigenvalues. You can have one eigenvalue. Okay, even if the thing has one eigenvalue, as long as it's Hermitian, then it's going to be diagonalizable. Okay, and the proof relies on a particular lemma called Schur's theorem. Here it is. Given any n by n matrix A, there exists a unitary matrix U such that UHAU is upper triangular. Given any n by n matrix, there exists a unitary matrix U such that the guy is upper triangular. So this is sort of saying that any matrix is unitarily triangularizable. Okay, one doesn't use this word. There is no such word, triangularizable. But, any matrix is unitarily upper triangularizable. Okay? And what we're going to do is use that to show that if it's Hermitian, if further it's Hermitian, then it's unitarily diagonalizable. Okay. All right. Okay. So yeah, let me make a comment actually about this. that says that any matrix A, right, you can have, this is going to be upper triangular, right? So what does that tell you about A? That tells you that A looks like A UT U inverse. Right? So any matrix can be decomposed into a unitary matrix, a triangular matrix, and the inverse of the unitary matrix. Okay. Remember that the inverse of a unitary matrix is the conjugate transpose. So, so this thing here is called the Schur decomposition of A. Okay, that you've basically factorized it, right? You factorized your matrix into a product where you know the middle guy is triangular, and you've conjugated it by a unitary matrix. Okay, so that'll be a consequence once we get Schur's theorem done. Okay, so okay, so let's see if we get Schur's theorem, and the proof is going to be by induction. Okay, so in the case n equals 1, right, you know, given a 1 by 1 matrix, we're looking for something you can conjugate it and make it upper triangular. Well, it already is upper triangular, right? So you can conjugate it by the identity matrix, say, right? So in the case n equals 1, it's trivial, right? So case n equals 1 is trivial, right? So as usual, assume the statement is true for k by k matrices, and let A be a k plus 1 by k plus 1 matrix. Okay, and we're going to look for a way of diagonalizing this guy unitarily. Okay, so here's what we're going to do. Let lambda 1 be any eigenvalue of A. Okay. And let W1 be in the corresponding eigenspace. Okay. And let's normalize it. Let's just assume that the norm of that thing is 1. If it's not 1, you just normalize it. It is possible to, and this is using the Gram-Schmidt process, which we skipped in the last chapter. It's possible using the Gram-Schmidt process to create an orthonormal basis starting with W1. Okay, right. You know, if you have any set of linear independent vectors, you can complete that to a basis, right? You just throw in, you know, throw in more linearly independent vectors until you have enough to span the whole space, right? But in fact, so that's sort of what you're doing. You start off with this one vector, and then you complete it to a basis, okay? But then you start chopping off pieces of the other bases, of the other basis elements, until each one of them is perpendicular to each other. Okay, and that chopping off business is basically this Gram-Schmidt process. It's not that exciting. Maybe we'll show it later. In any case, you can do it. So you start off with your guy. you complete the basis, and then you chop off everything in such a way so that the basis turns into an orthonormal basis. Okay. So let's call that an orthonormal basis, which we'll call W1 WK plus 1, because we're in R case. Mia, what's your question?
What's normalizing again?
Normalize means just divide by the magnitude.
Oh, okay. So it equals 1.
Yeah, so that the magnitude of the new guy equals 1.
Okay.
Okay. So using the Wi as columns of a matrix, we obtain a unitary matrix, which we'll call W. Okay. So let's think. What's the first column of WHAW? So you take your basis, you take your matrix A, and you take WHAW. Right? What do you get? What's going to be the first column of that? Anyone guess? Remember what W is, right? W is the guy with these guys as columns, okay? And then WH is going to be W1 conjugate, right? You take the conjugate transpose. Take the conjugate transpose. Or maybe let's say it this way. Suppose I multiply by the inverse of this guy. Right? The inverse of WH. This is a unitary matrix, so the inverse of WH is just going to be W, right? So I get, if I multiply on the left, I'm going to get W1, WK plus 1, I'm going to get W here, times some matrix, right? And I'd like to know what can you tell me anything about that first column?
Would you get lambda 1
And then
0?
and 0 is all the way down. Yeah, you get lambda 1 and 0 is all the way down. Great. Right. You're going to get lambda 1 and then 0, 0, 0, 0, 0. Right? Because you know that A is going to act on these guys column-wise. So the first column here is going to be AW1, right? So if I want to get an AW1 in the first column, right, that's to say lambda W1. Right? The only way I'm going to get that in the first column is if my first, the only way I'm going to get that lambda W1 in the first column of this product is if I have lambda 1, 0, 0, 0, 0 all the way down. Right? Because then I'm going to multiply that first row by lambda 1. Right? Can I see that? Okay. Any questions? Any questions about that? Okay, so just by your knowledge, again, it's your knowledge of how matrix multiplication works that we use over and over. So you have to know how matrix multiplication works, but that's how it goes. Any questions? Anyone confused by this? We've seen something very similar before when we talked about diagonalization. Okay. So okay. So the first column is lambda 1, 0s all the way down, right? And then we have some stuff. I'm not going to care about what's up here in the first row, but I'm going to call everything else. I'm going to call this this k by k matrix here M. Okay, so that's great, right? Maybe now you can almost see the end, right? We have this W, H A W, right? Using our one eigenvector, right? Using our one eigenvector W1, we create this matrix so that if it basically diagonalizes or triangularizes the first part of it. Right? And then what are we going to do? We've got a k by k here, so we're going to use induction, right? We'll use the inductive hypothesis. Right? So, right? You say, well, okay, right? I know my induction hypothesis. I know that there exists a unitary matrix that's a k by k. Oops. There's a k by k unitary matrix such that V1 H M V1 is upper triangular. Oops, that's not V1. There's this guy, a k by k matrix called V1. So let V, I should have been using C's instead of R's all along, right? Because we're talking about complex matrices. So let V be a k plus 1 by k plus 1 matrix. By taking this guy, right? It's going to be 1 all the way zeros here, and it's going to be V1 here. You know what we're going to do with that, right? We're going to take W H A W, and then we're going to conjugate that guy by V. Right? That's going to be lambda 1, 0s all the way down here, and then some stuff here, doesn't matter. And then here you're going to get V1, H, and V1. B1H and B1 is upper triangular, right? So the whole thing is upper triangular. So we have conjugated A by this guy WV, right? And we end up with an upper triangular matrix. And so we just need to make sure, is WV unitary? And it is, because if you take WV H against WV, you end up with VH, WH, WV, and this is the identity, and this is the identity, which is odd, since W and V are unitary. And what we see is that a product of unitary matrices is still unitary. B was unitary. Okay, so that's the end. So that's the end of Schur's theorem. You see that we were able to find a unitary matrix, WV, so that if you conjugate it, you start off with your arbitrary matrix, right? This was just any old matrix. It didn't have, there's no conditions on it. Start off with arbitrary matrix, and we found a way of conjugating it and getting an upper triangular matrix. So this gives us the Schur decomposition of any matrix into a unitary conjugate of a triangular matrix. Any questions? Any questions? Feel free to ask questions. Yeah, we've got plenty of time. We're moving fast enough in this course. Any place you're confused. So think, we're going to do it by induction. We're going to do it by induction. So case n equals 1 is easy. So let's assume it for the k by k's. Take a k plus 1, k plus 1. And then you see how we drop down to the k plus k case, right? We take a single eigenvector, right? And then we make, out of that eigenvector, we make a matrix, so that if we conjugate by that matrix, we diagonalize the first column, right? We diagonalize the first column. It doesn't become upper triangular anywhere, but we do triangularize the first column, right? That reduces the problem to a k by k, right? Then we already assumed that the k by k could be solved, and we use the thing that solves the k by k to create a matrix which, when we conjugate this thing, it makes this thing upper triangular, right? And then we just check that right? So we take that WHAW, and then we conjugate it by B, and we end up with this thing, which is upper triangular. Okay, Anna.
Yeah, so over there,
Yeah.
You said that we don't care about what's in the first row.
That's right, because we're going for upper triangularity. Right?
Yeah, but how do you move on from that to the next one where everything in the upper row is 0 except?
We made that, right? So this is what we get, and we are really hoping that we can make this thing upper triangular, Okay, so what we do is we create another thing, right? So that if we take this thing, right, and put it on this, and conjugate this thing by this thing that we just made, then we get an upper triangle. Okay. So we made this. We can, you know, we can make these zeros because we're making this thing. That's up to us. Okay. Okay. So so that gives us the Schur's lemma, Schur's theorem. Excuse me. Schur's lemma is something else. And so Schur's lemma actually gives you the proof of the spectral theorem immediately. So proof of the spectral theorem. Let's suppose that, say that A is Hermitian. Suppose that A is Hermitian. We know by Schur's theorem. Schur's theorem says there exists a unitary U such that U, H, A, U is upper triangular. Right. We know that any matrix can be turned into an upper triangular one. Okay. But, however, observe. If I take the conjugate transpose of T, right, what I get these guys in the opposite direction, right? UH, AH, UH, H. Okay. But A is Hermitian, so that turns into A, and of course UHH is just U, and so we see that this triangular matrix is actually Hermitian itself. T is itself Hermitian. Right? So, yes?
Why is it, when you take the Hermitian of something, you have to reverse the order?
It's, you remember, it's, what's the Hermitian? When you take, you're taking the conjugate transpose.
I just don't get why it goes from UHAU, like the Hermitian of that, to UHAH, UHH. Why isn't it UHHA, HUH?
Say it again?
I don't get between the first step and the second step. Like, why is the first U not UHH?
Well, just remember back when we did transposes, right? What was the transpose of AB? Is B transpose A transpose?
Oh, okay.
Right. So that's what we're doing here. The transpose of ABC is going to be C transpose B transpose A transpose. That you do in the reverse order. And you know we've certainly got conjugates on here, but the conjugates don't affect the order. Okay. So T is itself Hermitian, right? T conjugate transpose is equal to T, right? And T is an upper triangular matrix, right? T is an upper triangular matrix. So what does that tell you? T conjugate transpose equals T, and T is upper triangular, right? So everything below here is 0, right? T looks like this, T11, T22, Tnn, and then there's some stuff over here. So if we flip it, we flip it and take the conjugate of it, we get the same thing. So what? So what does it tell us about this stuff?
So
it's all 0, right? Because when we flip it, we get 0, so that these guys had better be zeros, right? Okay, what does it tell us about the diagonal? That when we flip it and take the conjugate, we get the same thing. They're all real numbers, right? Actually, that we don't really care about that. But in any case, what we get is that t is diagonal. The important part is t is diagonal. I mean, it's also real, but a real diagonal matrix. Okay. So every Hermitian matrix is diagonalizable, is unitarily diagonalizable. That's the spectral theorem. We've shown it. And we've also shown that T is going to be a real matrix, but you could have guessed that because we already knew that the eigenvalues of a Hermitian matrix are all real. So when you diagonalize it, of course, you're going to get real eigenvalues down the diagonal. I should make a comment. I don't know if we'll do this, but there's also one also has an analogous theorem for symmetric matrices, real symmetric matrices. That any such matrix is orthogonally diagonalizable. That you can find an orthogonal matrix. In other words, a matrix consisting where the columns form an orthonormal basis, such that when you conjugate by that guy, you get a diagonal matrix. So there's a real analog of this, and I think they go into it. The proof of that is actually a bit more tricky than the complex one, and they do it in the text. But I don't know if we will. Okay. So I'm gonna stop here for today. So the next thing we're gonna do is talk about. There's actually a class of matrices where we can actually answer the question of being unitarily diagonalizable completely. So what we'll find something that you are unitarily diagonalizable if and only if you're this kind of matrix. Okay, and that's called a normal matrix. So it's being Hermitian is stronger than being normal. There's actually a condition called normal that's equivalent to this, and we'll see that being normal, that you're normal if and only if you're unitarily diagonalizable. But we'll do that next time, I guess.